Yeah, so the aim of this presentation was to provide, to collect different works that we have been doing related to climate services, working at different timescales from sub-seasonal, seasonal to decadal, focusing on energy. I was analyzing the different theses from the CAFE project, and most of them are focused more on the technical aspects of the predictions. So the aim of this presentation was to show a similar approach, but always thinking that our research on this field, it's tailored from a previous discussion with a user. Okay, so we have been doing similar things to the theses that have been developed in this project, but previously there were several discussions trying to understand, okay, here there is a gap, we need this kind of information, and we were co-developing with them something yeah, that in the end it was useful for them. So in all these works, yeah, many people from the department have been working. I listed here some of them, yeah, but many other people from different backgrounds, people with a background in physics, but also in economics, social sciences, everything have been, or also communication, have been working together in the last years on this field. Okay, first of all, short summary about BSC. So BSC, it's the Spanish supercomputing facility. So there is the Mare Nostrum supercomputer, and this is version 4, and sooner, I hope, we'll have version 5. And we provide services to the whole community. And on top of this, there are 4 different research departments, and we are working in the Earth Science department. In total, we are about 120 people working in air quality and climate. And we are organized in different groups. Yeah, and we are involved in different European projects, etc. Okay. What we do is we try to simulate the reality. So we work with observations, and we use mathematical models to reproduce the reality. We try to work at global or local scale, so taking into account the different questions, the different challenges, we adapt ourselves, and we work at different time scales. So the aim of this presentation was to explain different works related to energy. So we are familiar in our society working with weather forecast, but when we go to climate, usually we think about climate change. So this is a representation of the temperature in different countries and that it's evolving over the years. At the end of the slide, you will see that everything is in red due to climate change. But on top of this, every year it's different. There are years that the temperature is higher than normal, and years that the temperature is lower than normal due to the climate variability. Okay, now we see that almost everything it's in red. And this is for temperature, but the same applies for wind. For instance, this is an assessment from GRC. Where we can see the anomalies in general for Europe, but also for the different regions, for wind, and also for solar radiation. So this is important because both supply and demand are affected by climate variability. Okay, and the context of the energy sector is that the renewable energy has been increasing in the last years, and the plans that are within the Green Deal, on the decarbonisation applies to renewable energy, and there will be a huge amount of renewable energy. It has a challenge in our system in terms of energy security, because nowadays, if there is a period with a wind drought, there is a backup in our system through fossil fuels, conventional power plants. But in the future, we have to be smart. We have to be aware of how this variability will affect the energy to balance supply and demand. And yeah, for instance, this is an example of a period that affected UK. In the energy sector, for sure that the users that Carlo was mentioning, so they are used to work with observations. They use reanalysis. But when they have to think about the future, usually they use climatology. So it's an assessment of the past years, because they have their own observations. They invest a lot of money in these observations, and they know the specific characteristics and the specific climatology of their parks. But yeah, taking into account climate change and the increase of extreme events, maybe climatology it's not a good tool from now on, or something that we have to take also into account. It's the different kinds of different prediction systems. And here in this figure, what I try to represent, it's like from weather forecast to up to climate projections. So different decisions that are taken in the energy sector that takes into account the predictions of wind, solar radiation, precipitation, temperature, in the different processes. Also, it's important to highlight that when we talk about the energy sector, there are different kinds of users. There are the people that it's managing the grid, but also the people that supply energy to the grid, the people that it's in charge of the logistics and the maintenance of the park. So there are different kinds of users, and all of them at some point need some information that it's within this range. So in this presentation, I'm going to focus here on the sub-seasonal, seasonal, and decadal predictions. And this work has been done in different projects. So first of all, why we have some predictability? It's because climate predictions are climate models that solve the whole system. And so taking into account, even though the atmosphere it's chaotic, the atmosphere is in contact with the ocean, the snow cover, soil moisture, and this infers predictability in our system. Okay, so in this figure, it represents why and the relation with the different systems to infer the predictability. So at the beginning, so for sure, the first discussion that you have with a user is that they are used to work with weather forecasts, and so several hours or days ahead. And when you talk about seasonal forecast, the first thing that they are thinking on this kind of skill, and also on the time resolution. And this is not feasible. So there is, in all these discussions, there is an effort to explain them, how to work with seasonal forecasts or with climate predictions in general, and to balance the pros and cons of these predictions. Now I'm going to show different examples of different predictions for different events. Some of them were done in this project, S2S4E. And so we will start with a heat wave and a wind drought in Spain in September 2016. And we analyzed it with sub-seasonal predictions. So we analyzed the seasonal predictions that were available several weeks in advance for that period. Okay, this is the event. In that figure, we see in blue the climatology. Okay, so what can be considered normal, and the black lines represent the specific the specific observation for that time. So on the top we have the wind, and we can see how for the specific wind for the specific week of analysis, that the wind was lower than normal and the temperature was higher than normal. So this is a constraint for the energy system. So lower supply than normal from the wind, and combined with a increase of energy demand due to the use of air conditioning, for instance. And yeah, here we can see how this anomaly was observed in the map. And now here, what we can see here, it's the predictions that were available. Okay, 1 week in advance, 2 weeks in advance, 3 weeks in advance, and 4 weeks in advance. And each PDF represents the distribution of the ensemble members that are in yellow. And yeah, the observations here in purple. So what we can see here, first, when we analyze the forecast, it's important to have information not only about the forecast itself, but also about the skill of this prediction. So in this case, we see, for instance, lead time 1 week. Yeah, the skill was low for wind, but yeah, there was some skill. Week 2, the skill was really low, and week 3 and week 4, it was really low. So it was negative. So it's better not to use the forecast. But when we analyze the forecast, we saw that the wind was so we distributed the analysis on terciles, and in the end, the reality was that below normal, while most of our predictions were showing that it was above normal. So in this case, a clear majority of the members were showing that the tercile that was not the appropriate in the end. And when we discuss with a user, it's important to be transparent on this and trying to analyze events and periods that can be relevant and trying to understand the results. So in this case, we were showing a prediction that was not useful at all for them, but it's a way also for them to understand what we are talking about. And then for the same event, for temperature, the results were much better. So the skill was higher. And as we can see here, 1 week in advance, it was clearly assessed, the extreme, but also several weeks in advance, it was predicted. Okay. Then another example. In this case, it's for US, working with seasonal forecast in 2015. Here we can analyze the wind anomaly that affected most of the country for wind, and here we can see that it was not only for one specific week, but it was for several weeks in a row that this anomaly was observed. And in the end, this period had a huge impact on the energy sector. So we analyzed this period with the seasonal forecast. And again, the results were not quite positive. So the most likely tercile was below normal as it was observed, but there was not a huge signal on this. So a user in the end, when we talk about this, when we show these results, so they expect higher signal to take decisions. So even though in this case the forecast was showing the tercile in the end, I think that they will not use it for any decision in this case. And something that was also important in this event, it was that it had a huge impact in the company, in the sector, and for them it was important to understand what was happening here, not only to understand the specific event, but also thinking on when it will come again. Okay, So in the news, yeah, they were talking about, they were trying to relate it with El Niño, because on that event, yeah, there was a Niño signal. And it's true that when you have El Niño, yeah, the winds in North America are lower than normal. So what we did in that case, it was to initialize the seasonal forecast with different initial conditions to assess if this event was due to the Niño, or if there were some other potential causes behind. Okay. Something that I want to add here is that usually when we interact with a user, we try to use all the information that is available. In all the other plots, we are using the seasonal forecast from Copernicus, the subseasonal forecast from S2S, from SABEX, from NSEC directly. In this case, we were using Easy Earth, and we were running it in-house, assessing different initial conditions. The reasons behind working with the information that is available is that within the concept of climate services, it's important to demonstrate that what is available, it's useful. And also to facilitate transparency and a replication of the results. So it's important to work with the information that is there. So in summary, coming back to the point, yeah, we were analyzing different initial conditions to assess the causes of this wind drought. And we saw an anomaly here in the temperature on top of the El Niño event, that in the end, it had an impact on the winds in North America, especially in the West Coast. Okay. And then also something that I want to show, so in the first case, we were working with subseasonal, now with seasonal. And in this case, I want to introduce also decadal predictions because it's quite novel. So decadal predictions are between seasonal predictions and climate projections. Together with seasonal and subseasonal, they are initialized simulations, but they have also boundary conditions problems, and their source or predictability are a bit different. So the Atlantic multi-decadal oscillation is the main source of predictability. And there are different groups working on this field, but taking into account the applications, it has been quite challenging. So we started to work with the wind 2 years ago, and we need to continue working. So what we were doing, it was first to assess the skill of the different systems that were available, to analyze the skill, taking into account different metrics, probabilistic, and also the deterministic skill scores. To be able to, in the end, to provide a prediction. But so first, it has several challenges. First one, it's that only a few systems, these ones that we have here, had wind, because we need the components of the wind. Sometimes in these models, in the end, they store only the average of the wind speed, and this is not useful for us, or the average of the components, and we need to calculate wind speed. But then taking into account the models that were keeping the wind, only one of them was in operational mode. So we did the same analysis only for Easy Earth in this version, because it was operational, and for the kind of discussion that we needed with the user, we need an operational system. And here we can see the result of the system. So here we have the hindcast in tercile, and we can see the signal of the model, and also here the prediction for yeah, for this region in the States. Then, yeah, when we interact with users, there are different levels of users. So people that it's potential users, people that it's more or less interested, that they have some knowledge about physics, metrology, and then there are other kind of users like the people from agriculture or energy that, yeah, they have people with a background in meteorology and climatology, and they are people that, yeah, that it's more easy to interact with them and to define new challenges. But at the same time, they also try to define challenges that sometimes are not feasible. One example, if they ask for some specific indicators or some specific variables that it's not feasible. One example, it was this case study in Romania. So it was an icing event. So when icing, it's a mesoscale process in quite local, and it has two main impacts. So it has the impact in the infrastructure, okay, because the machine cannot work, but also in terms of logistics. So it's impossible to access to the park, and yeah, during this event, as we will see below, there was much wind than normal, but yeah, all the plants were stopped because they cannot restart the production. And the user wanted to have a subseasonal prediction of icing. And yeah, we tried to explain that it was not feasible. And in the end, yeah, we were discussing together. We showed the predictions for temperature. It was not enough for them. And in the end, yeah, we ended up also providing extremes of temperature. Okay, so it was a balance between their demand and what's feasible from the scientific point of view. Okay, so yeah, the event here, yeah, we can see the extreme of temperature. The anomaly, so for wind, it was higher than normal, as I said, but the problem was not here because the problem was that the anomaly on temperature was so high. And yeah, and we provided the forecast for temperature and also for minimum temperature, okay? Then another example of indicator, it's for the wind energy. So the wind speed, it's useful for them, but taking into account the specific ways of that the windmills are working. So when we have a wind speed of 0, yeah, nothing, yeah, the windmill is not working. But then there is this speed, the cutting speed, that's at which speed the windmill starts to produce electricity, and then it increases with the speed until one specific point that it's stable until there is the cutoff. Cutoff means that they stop the system to avoid problems and with the system. So a way to integrate all this, taking into account the different, this is specific for this kind of power curves are specific for each kind of windmill. Also, there are different types of windmills in terms of the altitude of the hub height and everything. So a way to combine all this was to estimate the capacity factor. The capacity factor, it's an average of the power output divided by the total power that it's feasible with this turbine, and it was an indicator that it was useful for them. So, for instance, yeah, here we have different power curves for different models. Here we have the models, and yeah, and we can see the power curves, and we integrate. So we define it and indicate different indicators taking into account these thresholds, and for instance, for the case of US that I was showing before, we provided the wind, and also we calculated the capacity factors taking into account the different power curves. Okay. Then also something that we try to do in these slides, I was showing RPSS and other statistical indicators that help us to assess the skill of our predictions. But for a user, this is not useful. And we have been working to provide an economic assessment. So understanding the kind of decisions that they have to take, and quantify the potential use of or the potential benefit of these predictions from the economic perspective. I cannot show the final results because it's confidential, but I will explain the methodology. Okay, so for instance, this was by the end of 2021, so before the crisis between Ukraine and Russia. Yeah, the renewable energy had a huge impact on the prices. Now, yeah, everything is a bit different. But we can see here, for instance, in the Iberian market, yeah, that this was an event with a lot of wind, so the prices were quite good. While in UK, there was a wind drought, and the prices were higher. And so we try to discuss with the users this kind of situations, taking into account the prices of the market, anticipating with time in advance this kind of events. Okay, so the first that we did, it was to analyze the different kind of decisions that in the energy sector they are taking in terms of trading and in terms of hedging. These are the two main decisions that are considering subseasonal and seasonal predictions. And taking into account these kind of decisions, yeah, we were analyzing the specific prices time in advance. So for instance, this was for another case study that we were analyzing in the project S2S3. The load in France for 2018, that there was a significant event, and in this figure what we can compare it's the specific load for 2019 compared to an average of 3 years of 2015, 16, and 17. And the same figure, but with the prices. So we were playing with difference in the prices, taking into account how good or bad were the predictions. Okay, as I said, I cannot show the results because it implies the use of data that I cannot share, but just to illustrate the point. And then also something that we did in this project, we did a huge effort, not only to assess past events, but also to work in real-time conditions and to synthesize all the information that was there to produce an operational tool. So for 1.5 years, we were putting together subseasonal and seasonal predictions for essential climate variables, but also for different indicators that I was showing. Trying to have a continuous interactions with the users. We were also providing outlooks to different users, and here we have an example for temperature. This is the same variable but with seasonal timescale. So for instance, something that for us it was important is that if we were analyzing the skill of the predictions, and if we know that the skill was lower than the climatology, we didn't show the predictions. And we did also a huge effort on how we show the information. So this is, for instance, for precipitation, we changed it a bit, the colors. So the tool, it's still available, but it's not updated nowadays. So in summary, some take-home messages that I think that it's not needed to repeat. But again, regarding future work, something that we are doing now, here in this presentation, I was showing results for subseasonal, seasonal, and decadal. From the scientific perspective, we work with different models, systems, and sometimes also in different communities. But for a user, this is not useful. So users, they want to see to different time horizons to have the same information. So something that we did in S2S4E, in this platform that I was showing, trying to show the same kind of information, but in the end, we were working with different models. Something that we started to work now, it's in seamless prediction. So to combine different systems to provide, to improve the predictability in these ranges. And also something that we also are working with here, we have a PhD student that was participating in the S2S challenge. It's working with artificial intelligence techniques to post-process some specific, to work on some specific post-processes on the workflow that we have. That's all. Thank you. Questions?
Thank you very much for a very interesting talk. And I always start with a very difficult question. Based on your experience and the current energy crisis, what recommendation would you give to policymakers to build a more robust system for the future in terms of energy, both production and consumption?
Well, it's a difficult question because, for the companies and for the different sectors, it's not easy to change a specific methodology that it's already working. So, for instance, ENSOE is like the aggregation of the different transmission operation systems, like here in Spain, Red Eléctrica, or and there was an agreement, and in the end, I think that it's I don't know if it's a law or it's a notice for the European Commission, to start using seasonal forecasts and to include climate variability on their assessments. But it's not easy to this kind of changes. Now that as we are pushing for the decarbonisation, where the renewable energies are going to be huge, there will not be an option to back up all the system on conventional power plants. So we have to be smart on the use of the systems that are available, and also on the integration of electric vehicles, and to see them as a potential battery for the whole system, like this concept, I think it's called vehicle to the grid, or this kind of thing. So it will be a combination of different things, because we need to change the paradigm.
Thank you. So there's nothing on Zoom so far. So first question, if I start with Carlo.
Thank you, Albert, for the presentation. My question was about the decadal case that you showed, because one of the lesson we learned from the decadal work that we did for energy was that the best predictor for hydropower, which is different, wasn't the precipitation, but was rather a statistical regression out of NAO pattern or the like. Have you tried to look at those large-scale feature for wind, or do they add any value? Thank you.
Yes, but as I said, so so for wind, for instance, there is a huge relation between the North Atlantic oscillation and the wind in Europe. Okay, so this relation it's clear, but the way that the system is reproducing the NAO with decadal, it's not so good. So here we have to we are analyzing different teleconnections to find a proper solution on this. So we didn't get the solution yet. So we were analyzing different teleconnection patterns.
Thank you. So next question, that here.
Yeah, I have one question about the wind drought forecast. That you showed the plot and how many ensemble members are used, and does the observed anomaly of wind falls into the ensemble spread?
But you mean with in these figures that I was these figures? Here we were using the ones with the seasonal. It's from Copernicus, and I think that it's 25, right? And with subseasonal, at the beginning we were using NCEP, and then we were granted to use in real time the S2S, and we were using the multi-prediction system from the European Center, and I don't remember the number of members at that time.
Okay. And each ensemble showed that anyway that the 1 month lead forecast is relatively better than 2 months and 3 months, but it looks that the observation is still outside of the ensemble spread, right?
Yeah, because we are in these cases I was showing some extreme events, and so these extremes are only feasible to be reproduced if the anomaly that produced this extreme it's resolved or not. So in this case, this is for wind. Yeah, it was not easy to reproduce, but for temperature, for instance, yeah, it's more easy.
Yeah. Emilio.
Hi. Thank you. You seem to be in close contact with final users. I have a question. It can be also a question for the previous speaker, Carlo. Can you estimate the amount of resources in workforce or in financial resources devoted to, for example, to hard science algorithms modeling, or to visual graphics, visual interfaces, or the time devoted to interaction with the final customer? I mean, can you estimate which part is really more take you more time, more resources, and more money?
From maybe their answer it's different, but in our case, it's difficult to estimate because we don't see these as different groups working independently, and we try to work together. So, and in this process, yeah, there are many people with different backgrounds together. So I will say that for instance, in this project, in the S2S3 project, that it was like climate services, working with them, I will say that it was 50-50. So more or less the people from communication, user engagement, user experience, all this, yeah, more or less 50-50 with the people with a background in physics. This was from our side.
Thank you. So next question. Alvaro.
Thank you. I think I didn't fully understand the example in which you were showing some project that was confidential. So maybe for that reason I didn't understand, or maybe it was my fault. But of course, when you are dealing about energy, meteorology is very important, of course, for energy, and you try to provide meteorological predictions. But my point is, up to what point one could not try to predict meteorology, but try to predict, for example, the price of the energy? Is this feasible?
As far as I know, in energy companies, they have a trading unit, and there is an expert on social events or like conflicts. There is an expert on weather. There is an expert on different industries. Let's say that there is a specialist for nuclear, for gas, all this, and they work on this all together. So I have never been in this kind of tables, But every day, there is a meteorologist that analyze what's new, what's available that day. They provide an assessment, and then there are different discussions. But yeah, how the decisions are taken, I don't know.
So the prediction of the price of energy is done by the company, by the private companies themselves. But there is no public center or somebody in Europe or elsewhere trying to provide public prediction for the.
Well, there are companies that SMEs that provide services on this, but they don't share this information, because in this case the information is the king. So it's a lot of money behind these kind of decisions.
Yeah, but that's my question. There should be some kind of public initiative for us, for the people or for the citizens, to try to know which would be the price of the energy. I don't know, 1 month ahead or 6 months ahead or something like that. I mean, this is very valuable for companies, but also the citizens should be able to know, to have this information. So in the same way that scientists predict the weather, we scientists should also try to predict the price of energy and energy consumption and all that.
But the price of the electricity takes into account many different variables. So if we take into account this year, at the beginning of January, the algorithm that can compute this price has changed a lot in the middle of February. So yeah, so it's.
Do you mind? Do you mean that it is much more complex to predict the price of the energy than to predict the weather? Really?
Yeah.
But this is because you are meteorologists or climatologists.
There is a reason why the market is much more difficult to predict, and it's because your prediction has an effect on the market, while meteorology is not the case. So, and people are making money out of it. So if there is a predictability, then it's exploited, and this removes the predictability.
Okay. So, Josh?
If I can ask a slightly provocative question that I think probably follows on from that line of thinking, is it actually a public good to help hedge funds predict energy prices better? You know, like obviously, like a lot of the things we're talking about here, really useful, you know, predicting icing on wind turbines and droughts and so on, but helping hedge funds get a better margin on energy prices, I sometimes wonder if is that actually good for society? Is it the sort of thing we should be doing as public organizations? I'd ask the question.
I don't know. I don't have a specific answer for this.
Okay. Anyone who wants to follow on that question? It's a really interesting discussion point, and especially for a group of young scientists where to think ahead. Hello.
I think it's a good provocation. Well, I like to think we are not helping the hedge funders in particular. I think we are helping anyone who is willing to deal with the data, right? And you have if you have the skill set and the tools to do it, and you happen to be a hedge funder, so be it. But you know, I think there are many others who are in similar situation, and some of them can be public institutions. So depending on the sector, I think so it's a bit of a loaded question, the one you're posing, Samar. But I don't think it's entirely fair to say that we are helping the hedge funder in a sense. I think we are helping anyone. Is lowering the access to the information, I would think.
Next question. Yeah, Christina.
There are many questions.
This is just a comment. Remember that a few years ago, there was €1 million prize for predicting the energy consumption in France. Remember, you had a talk and I had a talk too. And the winner was not someone that used artificial intelligence. That's all.
Any other question from the audience? Otherwise, I have a general question for the speakers this morning, and thinking ahead about artificial intelligence and this more sophisticated data mining tool. what recommendation would you give on overfitting results from this one, or overfitting in terms of looking at predictors and then building a predictive model? Because we can look a lot on linkages in a reanalysis data set, but how to be careful in interpreting these results?
In our case, so if I correctly understand the question, so we always try to analyze it with the analysis, with the observations, and then we analyze if this transition. It's also the same in the forecast, working with the hindcast. And yeah.
And any other comments? So is it time to break for lunch?
Just a speaker, so maybe some question was missing to the other speakers in the morning, in which we had less time. So maybe we could go back to the morning if some question was. If somebody wanted to make a question in the previous session and there were no time, now is a good time because we have still 5 minutes to go for lunch. If you want to make a question to any other of the previous speakers, or if not, okay. So if there are no further questions to any other of our speakers in the morning.